Okay, let's dive into black holes. I mean, just the name itself. It sounds like science fiction, doesn't it?
Absolutely. So extreme. But they're actually a core prediction from Einstein's general relativity.
Right, they really push our understanding of, well, everything. Physics, space, time.
Exactly. And looking at the material you shared, our plan today is to, cut through some of the complexity.
Get straight to the essential facts. And maybe some of the more surprising bits?
That's the idea. A quick deep dive into what makes these things tick.
Okay, so first things first. How do they even form? The sources talked about that.
Right. So the most common type we think about, stellar mass black holes. They come from giant stars dying.
Stars are much bigger than our sun, yeah.
Much bigger. When they run out of fuel, the core collapses. Gravity just wins.
And if that core is heavy enough, maybe 3 times the sun's mass or so.
Yeah, around that threshold, if it's dense enough, nothing can stop the collapse. It just keeps going.
Down to a single point, the singularity.
That's the prediction from general relativity, yeah. An infinitely dense point. The star's outer layers might go supernova.
Big explosion.
Huge. But the core itself just collapses inwards forever.
And the material we looked at mentioned others too, not just these stellar ones.
Oh yeah, definitely. The supermassive ones.
The monsters at the center of galaxies. Millions, billions of times the sun's mass.
Exactly. How they formed is still a bit debated. Mergers, maybe.
Yeah.
Or giant gas clouds collapsing early on.
Still some question marks there.
And then there's the theoretical kind. Primordial black holes.
Tiny ones may be formed right after the Big Bang.
Potentially.
Well,
We haven't found direct proof yet, but it's an intriguing idea based on the physics.
So, okay, they've formed. What are they actually like? Structurally, it's not like a planet with a surface.
Not at all. No solid surface. You've got that singularity right at the heart.
The infinitely dense bit.
Right. And around that, the crucial part, the event horizon.
Ah, the point of no return. The ultimate one-way street.
That's a good way to put it. It's not physical. More like a boundary in space-time. Cross it, and you're not coming back.
Not even light.
Nope. Escape velocity becomes faster than light. And the source material also mentioned the ergosphere.
For rotating black holes, right. Where space-time itself gets dragged around.
Yeah, frame dragging. It's a really bizarre consequence of general relativity. Space-time isn't just a stage. It's an active participant.
Mind-bending stuff. And the sources were clear. They don't just suck things in like a cosmic vacuum cleaner.
Correct. It's gravity. Just incredibly strong gravity. Like any mass, they attract stuff.
But close up, that gravity warps space-time so much.
That past the event horizon, all paths just lead in. There's no way out.
And their influence on the universe around them is pretty dramatic.
Oh, hugely. Their gravity bends light, creating gravitational lensing. We see distorted images of things behind them.
Like a cosmic magnifying glass almost.
Kind of, yeah. And when matter falls towards them.
It heats up. That's how we often find them, right? Since they're black.
Exactly. Material spirals in, forming an accretion disk. Gets incredibly hot. Shines brightly, especially in X-rays.
And sometimes they shoot out those massive jets.
Yes. Powerful jets of plasma near light speed. Probably linked to magnetic fields tangled up in that accretion disk.
Okay, and we have to mention the famous one, spaghettification.
Slight chuckle.
Yeah.
Right. The tidal forces get too close to a smaller black hole, and the difference in gravity between your head and feet.
Stretches you out like spaghetti.
Pretty much. Tears you apart. Though, interestingly, for a supermassive one, the tidal forces at the horizon might be gentle enough you'd cross it before. Well,
Before the spaghettification happens. Grim thought.
it is. And this all leads into the big theoretical puzzles they pose.
Like general relativity predicts them, but then the theory itself kind of breaks down.
Right at the singularity. Infinite density. Our current physics, GR, can't really handle that. It signals we need something deeper.
Like quantum gravity, a theory that unites gravity with quantum mechanics.
That's the hope. And then Stephen Hawking threw another wrench in the works.
Hawking radiation, the idea that black holes aren't completely black.
Exactly. Quantum effects near the horizon mean they can actually emit particles, lose mass, and eventually evaporate over immense timescales.
Which was revolutionary because it connected black holes to quantum theory and thermodynamics.
And led directly to the information paradox.
Ah, yes, the big one highlighted in the sources. What happens to the information?
If a black hole swallows, say, a book, the information in that book seems lost when the black hole evaporates via Hawking radiation.
But quantum mechanics insists information can't be truly destroyed.
Precisely. So does the information get out somehow? Is it lost forever? This clash between GR and quantum mechanics is a huge, huge mystery.
So wrapping this up, why should you, listening now, really care about these distant, strange objects?
Well, as the sources really drive home, they're more than just curiosities. They are nature's laboratories for extreme physics.
Testing grounds for our most fundamental theories.
Exactly. Understanding them means understanding gravity, space, time itself at the deepest level. They force us to figure out how gravity and quantum mechanics fit together.
Okay, so quick recap. We touched on formation collapsing stars, supermassive giants, maybe primordial ones, their structure, singularity, event horizon, ergosphere.
Their powerful effects, gravity, lensing, those bright accretion disks, jets, and yes, spaghettification.
And the big theories and challenges, general relativity, Hawking radiation, and that nagging information paradox.
It's clear from this deep dive there's still so much we don't know. They keep challenging us.
Absolutely. And maybe the information paradox is the thing to leave you pondering. Does information really vanish forever once it crosses that event horizon? It's one of the biggest unanswered questions out there.